Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to the Earthquake Seismology course in Module 6. In the lecture 4 today, we are going to cover the concepts such as the core phases. Especially we will be talking about reflected core phases, refracted core phases, diffracted core phases and additional core phases we will be covering. And then we will be having the summary of today's lecture. As far as the recap of previous lecture is concerned, we learnt that the travel time data are generated by combining data from numerous earthquakes all across the globe from different epicentral distances. We also learnt about the earliest model of velocity structure in the earth, that is the Jeffrey-Bullen earth model, that treats the earth as a series of shells characterized by the behavior of velocity with depth. Some of the drawbacks the JB Earth model had was it could not resolve the near velocities in the inner core, whereas recent model consisting of higher resolutions had the finite S velocity in the inner core, which implies that it is solid. The seismogram shows the arrivals of different phases corresponding to body wave phases. We learnt about the various kind of phases that travels inside the earth. For example, we learnt about the PKI-KP phase, PCP phase, PCS phase, SCS phase, etc. We also learnt that there are the phases which have the minimum time for the travel, but there are the phases which also has the maximum time phases such as the surface reflections PP and SS, and we also derived that how these phases are traveling the maximum time inside the earth. Now let's talk about the core phases. As you know, the outer core is liquid and it has the lower velocity than the mantle above. So it is considered to be ideal for the seismological studies of the various core phases due to the differences in the solid mantle and the liquid core. The core mantle boundary is a solid liquid interface and it acts as a powerful reflector for the shear waves. The travel times and amplitudes of the core phases are also used to study structure near and within the core. So far, the reflected core phases are concerned. We also have seen the SCS phase in the previous lecture, which basically travels as S waves from the focus and then it reflected off from the core mantle boundary so that it has the small c within it, and then after the reflection it travels back to the surface as S phase. That's why it has SCS name within it. And there is PCP phase that we have also seen, which travels as P in the mantle, reflects off from the core mantle boundary. That's why it has C, then comes back after the reflection as P. That's why its name is PCP. There are some converted core phases that such as the SCP and the PCS. So if you look at the ray path diagram of the PCS, which is depicted in this particular figure here, you can see that there is this focus, the rays emerging out as P wave, then reflects off from the core mantle boundary. That's why it has a small c. Then it comes back to the surface as S. There are some multiple phases are also there, such as SCS2 and SCS3 and etc. So if you talk about particularly the SCS2 phase, then it bounces twice at the core mantle boundary and it also reflects from the surface once. So if you look at the diagram here, the ray path of SCS2, then you can see there is this focus from where the S wave is traveling down and then reflects off from the core mental boundary, so it has a small c, then coming back to the surface and having reflection once, and then after the reflection it travels as S wave, and then having another reflection from the core mental boundary, that's why there is c again, and then it's after the reflection it is received at the receiver here, so that's why it has SCS2. And this is the seismogram that is recorded at Tonga subduction zone in the region of Hawaii, and it has several SCS phases within it, and the corresponding ray path diagram is depicted over here. Now, if we talk about SCS and its prominence on the seismogram in comparison to PCP, the SCS is more clearer than PCP on the seismogram. It is happening because SCS is made up of two kind of vibration, SV vibration and SH wave vibrations. So SV vibration, when it travels down, then some part of energy gets refracted, that means transmitted to the outer core, and then some of the part of the SV wave energy gets reflected. But on the other hand, if we talk about the SH wave part of the SCS phase motion or S wave, then this part basically do not convert to the P wave in the outer core. When it travels down towards the core mental boundary, then it basically totally reflected, because no part of the SCS phase gets transmitted into the outer core. So major part of its energy gets reflected, so it is clearer or prominent on the seismogram. So SCS are sensitive to vertical average velocity for the mental. That means if you use SCS, then you can sample the vertical average velocity that it is going from focus to the core mental boundary and then coming back up. That means major part the SCS is traveling is within the mental. So it can give us the clue about the vertical averages velocity in the mental, and it is very useful to study the velocity structure of the mental. And the impedance contrast at the core mental boundary for the P wave is very small, that is around the 5% difference is there. That means if you go from mental to the outer core, then the impedance for the P wave changes only by 5%, which is happening because the P wave velocity decrement that is happening from mental to core, that is about 13.7 kilometer per second to 8.1 kilometer per second, which is offset by the density increase, that is around 5.5 gram per centimeter cube to 9.9 gram per centimeter cube. Now, if you look at this particular travel time curve, that is from IASP 91, then what you will observe, when the P wave start off from the focus and then it leaves from the focus at progressively smaller angles of the incidence, and then it bottoms deeper in the mental and so reach at greater distances. So this is your direct P phase here, and this direct P phase, when you will see, then this direct P phase gets basically merged with the PCP phase here. This is the phase that goes down and then reflects off as a P wave from the core mental boundary. So after a certain distance, both of the direct P waves and the PCP phase gets converged and becomes identical. Since this PCP phase is reflecting from the core mental boundary, so you can see that if we derive the travel time curve for PCP, then it will always be concave upward. So that is what it is written. Rays leaving the source at progressively smaller angles of incidence closer to the vertical bottom deeper in the mental and reach greater distances. As the bottoming depth approaches the core mental boundary, the travel times of P and PCP converge. That means PCP is having the concave upward travel time curve, and at certain angle of incidence P grazes the core mental boundary and P and PCP are becoming identical. Now the P wave, when it enters the outer core, then travels through it and refract into the mental, then it is known as PKP. So if you look at this particular focus here, you can see the takeoff angles are getting smaller and smaller as you go away from the focus. Then That means they are having the smaller takeoff angle progressively and hence having the larger distances at the surface. When you go from here to here, the takeoff angle is decreasing, but the distance that it travels on the surface will be larger. So up to 98 degrees, the direct P wave will be observed, and after you increase the angle even a little bit, then it will start to graze the outer core and the mantle boundary. Then it basically grazes that boundary and then it travels inside the outer core, that means the K part of it, and then finally it comes out in the mantle and then recorded at the receiver on the surface. For an angle of incidence slightly below grazing, PKP reaches the surface at point A at a distance close to 180 degree. Then after, rays that are having a smaller angle of incidence enters the core further, arriving at distances that are progressively closer to 180 degree until they reach roughly 145 degree. That means the point B, that is around 145 degree away from the source, and since as you are decreasing the takeoff angle, there is decreasement in the distance as well. That means they are having retrograde motion, and after B, as you decrease the takeoff angle further, then the distance will start to increase successively again. That means prograde motion you will observe, and this goes on for rays reaching distances up to C, that means 153 degrees, corresponding to the ray that grazes the inner core outer core boundary. So if you look at this particular travel time curve, then what you will observe here is that the ray that start to graze the outer core and the mantle boundary, then that will be recorded at the largest distance, that means at around 177 degrees, that is point A. Then after that, if you will even reduce the angle further, then it will start to come back and then record it at smaller distances. That means this branch of this travel time curve will be having the retrograde motion from A to B. Then if you will even decrease the angle, then it will start to record at higher epicentral distances. That means you will be having the forward branch, that is up to C, and then after C you will start to have this Pk small ikp and Pk capital IKP. Then if you will reduce the angle further, then the rays will start to enter into the inner core, then the Pk IKP phase will start to emerge out and the stations will record this particular phase. This branch will be having the epicentral distance at which it will be recorded will be from D to F. For the rays that are having the reflections from the inner core outer core boundary will be recorded as Pk small ikp, and this will be basically having the linear travel time curve and will be start to have the initial point C. So this is what it is written here. You can see for the core, the shadow zone occurs for distances between 98 to 145 degree for the P wave. So if you see this particular zone, this is the shadow zone for the P wave, which is around from 98 degree to 145 degree. No direct P wave will be recorded in this region by the station. So this particular region is known as shadow zone. And the AB branch, sometimes labeled as PKP, so this is your PKP phase here, is the back branch on which rays with a smaller angle of incidence appear at smaller distances. That means it has the prograde motion. The BC branch, this BC branch here, is the forward branch on which the rays with smaller angles of incidence appear at larger distances. So this BC branch will be having the larger distances for the smaller angles. So that is your prograde motion. In reality, body waves are observed in shadow zone. So the shadow zone that we were talking about between 98 to 145 degree, that is for the direct wave. But in this zone also you can also record the P wave energy or the body wave energy in the form of PP wave or PPP wave or SS wave. So much of the body wave energy arrives as surface reflected or multiply core reflected SCS2 or SCS3 etc. arrivals. Since the inner core has higher P wave velocity, other arrivals of the P wave that encounter the inner core also appear in the shadow zone. These phases are like Pki Kp and Pk small I Kp. The travel time curve does have a Pki Kp branch, that is D2F. This is your Pki Kp branch, and where D is the distance at which the Pki Kp is first observed. So this is the distance at which the Pki Kp is first observed, that is around 122 degrees here, and a back branch for Pk small I Kp. So this is your back branch, this one for the Pk small I Kp. Because the reflection occur at vertical distances, the back branch start at C. So this start at C, and where Pk small I Kp and Pkp are equal, and extends via D back to 0 distance. Hence, the portion of travel time curve containing CD and DF is due to the rapid increase of velocity at the inner core outer core boundary and is analogous to triplication. One thing that we must know is seismic energy also enters the shadow zone via P and S waves that diffract around the core. The ray path for the diffracted P wave is denoted by PD, that should be in subscript, and diff should also be in subscript. They start to diffract at a distance of around 98 degrees, or you can say 100 degrees. So you can see in this it is diffracting over here, and then it is starting off from around 98 degrees and then successively recorded at all the distances on the surface. Travel time curve becomes linear because all the diffracted waves bottom at the core mantle boundary and so have the same ray parameter and has apparent velocity. So it has the linear travel time curve over here, the diffracted wave for the P. Arrival times of the P waves recorded by International Seismological Center during the years 1964 to 87, and they have basically plotted this particular curve using at least 200 arrival times from different earthquakes from several catalogs. So what they observed that the PKP BC branch, this branch over here, BC branch is observed also beyond the 153 degrees. If you look at this here, in the previous slide we saw that this particular branch is having the termination or the last distance it will be observed is around 153 degree, but in reality it is observed beyond 153 degrees as well. That is maybe due to the diffraction around the inner core. Precursors to the PKP and DF branch, this is the DF branch, this one here, are observed that result from the seismic scattering at the CMB and in the mantle. There are other phases that also can be recorded as an additional core phases, that means the SKS phase and SKKS phase. So SKKS is similar to SKS, but it has one more reflection at the core mantle boundary. Because the P wave velocity of the uppermost core is not much larger than the S velocity of the lowermost mantle, SKS and the SKKS waves do not change direction significantly as they cross core mantle boundary. SKS and SKKS etc. are only waves that bottom near the top of the core and are used to constrain the outer core's velocity structure. So these basically the only waves that bottoms near the top of the core, and they are used to find the velocity structure of the outer core. There are the other phases such as the PKKP, PKP, PKKP, and there are phases such as PKIIKP, PKJKP. So PKKP is the phase that has the P wave which has underside reflection at the core mantle boundary. So this is the PKKP phase here. You can see that the ray is traveling as P wave. As soon as it enters the outer core, it becomes K, and then after the reflection from core mantle boundary, it travels as K again in the outer core, and then as soon as come out, it travels as P. So this is your PKKP. Likewise, there are PKP and PKP phase. So PKP phase is this one. So you can see that this phase is traveling as P here, and then as K, and then again as P, and then reflection from the mantle and the crust boundary, and then it travels as P, and then again K, and then P. So this is your PKP, PKP phase. It is also known as P prime, P prime phase, that is written here. There is another phase, that is PKIIKP. That means an underside reflection from outer core, inner core boundary. So this is your outer core and this is your inner core. So PKIIKP phase is this one. So you can see that this ray is traveling as P wave, then as K wave. As soon as it enters into the inner core, it becomes capital I. Then after the reflection from inner core, outer core boundary, then it travels as I again, and then comes out as K, and then travel as P in the mantle. That is PKIIKP. There is PKJKP phase. So PKJKP phase has a very weak amplitude and it comes very later into your seismogram. So it is very hard to observe. So this is the summary of today's lecture. Core phases can be challenging to study with travel time data because their travel time curves are complicated and some of the arrivals are small. Reflections of the core mantle boundary are denoted by a lowercase c. So SCS is an S wave reflection and PCP is a P wave reflection. SCS is a more perceptible, or you can say more prominent on the seismogram arrival than PCP because the liquid core does not transmit shear waves. K denotes the passage through the outer core, like PKP enters the core, travels through it, refracts into the mantle and reaches the surface. For the core, the shadow zone occurs for distances between 98 degrees to 145 degrees to the P wave. P waves in the inner core are denoted by capital I and waves reflects at the boundary between the inner core and the outer cores, giving the phases Pk small I Kp. Seismic energy also enters the shadow zone via P and S wave that diffracts around the core. We have talked about it in the slides previously. S wave going over the mantle and through the core as a P wave like SKS involves an underside reflection at the core mantle boundary. So this is all for today's lecture and these are the references. We will meet in the last lecture of module 6. Thank you so much. Bye-bye.